Hey everyone, welcome back to my channel. Today we're going to learn about factorization, which is the flip side of expansion of an algebraic expression. Now firstly, what are factors, or what is a factor? A factor is a number that multiply together, or numbers that multiply together to give a bigger number. So for example, 20 can be written as 2 times 10. So 2 and 10 are both factors of 20 because they can be multiplied to give 20, or 20 can be divided into 2 and 10. Similarly, 20 is also equals to 4 multiplied by 5. So 4 and 5 are both factors of 20. Let's take 18. 3 into 6 gives us 18, so that makes 3 and 6 both factors of 18. And 18 can also be written as 2 multiplied by 9, so that makes 2 and 9 both factors of 18. It is important to note that some numbers may not have any factors at all, which are also known as prime numbers, which can only be divided by themselves and 1. And examples of this include 2, 3, 7, 11, 13, 17, and the list goes on and on and on. So now what does it mean to factorize an algebraic expression? Well, factorization is essentially the process of breaking down an algebraic expression into its factors. So if we take this equation, for example, when we expand this side 7x plus 4, and we do that by multiplying 7 with x and 7 with 4, what we get is 7x plus 28. However, if I were to go from this side to that side, it'll be known as factorization. So going from this to this is expansion, and going back is factorization. So now first let's cover the factorization of linear expressions, which are expressions where the power of x only reaches 1 and it's never above 1. So examples of linear equations can be 2x plus 4, 7x plus 1, 3x minus 5, and it goes on and on. Any equation where the magnitude of x is never greater than 1 is a linear expression. And these are the easiest to factorize. So first let's take 2x plus 8. Now the way to factorize linear expressions is to look for common terms, or common factors actually. What is one common factor that both of these two terms have, 2 and 8? Well, it is that they are both divisible by 2. So we can also write this as 2 into x plus 4. And this is as far as I can factorize this. Now if I were to open this, 2 into x and 2 into 4, I'd get 2x plus 8, which is the same as this. Another example can be 3x plus 9. Now the one thing common between 3 and 9 is that they're both divisible by 3. So the one common factor they have is 3. So I can also write this as 3x plus 3. Now let's take a larger example. What about 16 plus 40x? Now, what is the largest common factor that both of these have? There are several factors that they have in common, including 2, 4, and 8. Let's just go with the largest one because it won't be further factorizable after we take 8 common. So taking 8 common, we get 2 plus 5x, and that's as far as this can be factorized. Now this is as far as the factorization of linear expression goes. Now what about the factorization of quadratic terms? Now quadratic terms are of course those where the power of x goes up to the magnitude 2. So for example, x squared plus 6x plus 9, or 3x squared minus 7x plus 2. All expressions where the power of x is 2 are known as quadratic expressions. Now the first way to factorize a quadratic expression is by completing the square method. Now firstly, what is a square? A square number, or a perfect square number, is a number that can be divided into two equal factors. So for example, 9 is a perfect square of 3, 16 is a perfect square of 4, 25 is a perfect square of 5. However, there are always numbers that aren't perfect squares, such as 10, 11, 12, 5, 6, 7. So in that case, and same is the case with quadratics. So in that case, we need to complete the squares. Now for example, this quadratic is a perfect square, and by that I mean that we can convert ax squared plus bx plus c from the three term quadratic. We can go back to the a plus b whole squared identity. If we can do this, it means that the quadratic is a perfect square. Now if I just write this as x whole squared plus 6x plus 9, which is also the perfect square of 3, we can see that this quadratic takes the form of an a square plus 2ab plus b square equation. So I can write the middle term as a product of 2x and 3. And now if I just collapse the entire thing, I'll get x plus 3 whole squared. So yeah, we can say that this quadratic was a perfect square. However, there are always quadratics which are not perfect squares. For example, let's take x squared minus 6x plus 1 for example. So now if I want to convert this into this form, I will need to make a few adjustments, and it will never be in this form exactly. There will always be a constant, and there can even be a multiple. So the first step would be to group the ax terms together in brackets, in square brackets. So let's just x squared minus 6x square brackets plus 1. The second step would be to add half the coefficient of x after squaring it. Add and also subtract. Now what I mean by this is we have x squared minus 6x and the constant we keep outside of the bracket, right? Now what we need to do is add and also subtract half the coefficient of x after squaring it. So half the coefficient of x is 3. So what we essentially do is x squared minus 6x, then we add 3 squared because 3 is half of 6, and we also subtract it to neutralize the effect of adding something, because we can't just add something to an expression without neutralizing it or balancing it out. And then you close the bracket, and of course your constant stays the same. So now what we have is this part of our expression, if you notice, is in the form of a squared minus 2ab plus b squared, where a is x and b is 3. So we can collapse this into x minus 3 whole squared, and this stays the same over here. Of course, it goes without saying that the sign in between these two numbers will also be the sign that your x coefficient has, plus 1. And now what you need to do is you need to take this constant outside of the bracket, and the way to do that is just to square it. So x minus 3 whole squared minus 9 plus 1, and x minus 3 whole squared minus 8. Note that the sign did not change because what we're doing over here is minus 3 whole squared. It's not minus 3 whole squared. The sign would change if it was minus 3 whole squared. What we're doing is minus and 3 squared. That's why the sign did not flip. And this is essentially all of completing the squares. We can make this into a separate step, saying take the form of the a plus b whole squared or a minus b whole squared identity and collapse the brackets. Now let's do another example on this. Now the one thing that we always need to make sure is that x square should never have a coefficient. We need to always get rid of the x square coefficient. Like in this example, x square already was free of all coefficients, so we did not need to factorize it first. Over here, however, in this question, x squared does have a coefficient, so what the first step automatically becomes to always factorize out the x square coefficient. And of course we do that by common terms or factors. So let's follow the first step we did in the previous question, in the previous example, which is to first isolate the x terms into parentheses. So this becomes 4x squared plus 8x minus 1. Then what we do is just factor out the common term, which is 4. It has to be 4 because we need to get rid of the x squared coefficient entirely. So this becomes 4x squared plus 2x minus 1, and then everything you do stays the same. So 4x squared plus 2x, half of 2 is 1, so we add 1 squared and then we subtract 1 squared, and our constant stays the same. Now again this takes the form of a squared plus 2ab plus b squared, so we can collapse this into one bracket. So this becomes 4x plus 1 whole squared minus 1 minus 1. Now in this example, taking this minus 1 out of the brackets is not as simple as just opening this whole squared. To take this out, what we need to first do is multiply by 4, because the order of operations says when you open parentheses you're supposed to multiply things. You can't just take it out without multiplying it, because 4 is being multiplied to both this bracket as well as minus 1. So we can write this as 4 into x plus 1 whole square, or let's just plus 4 into minus 1 minus 1. This bracket can be broken down into these two terms because 4 is individually being multiplied with both of them. And now it's as simple as opening the bracket into minus 4 and minus 1, and our completed the square version of our quadratic is 4x plus 1 whole squared minus 5. Let's just do one more example on this and we can move on to middle term breaking. So x squared plus 8x plus 10. Now the way to do this is the same as we've done the previous two questions. Isolate the x terms into x squared plus 8x and add the constant, of course stays the same. Then you add half of the coefficient of the x term squared. So it becomes x squared plus 8x plus 4 squared, and then you subtract it as well because you can't just make changes to the expression of your own accord. And again this takes the form of a squared plus 2ab plus b squared, where a is x and b is 4, and of course this middle term is the multiple of 2, x and 4. So you can now collapse this bracket into x plus 4 whole squared minus 16, of course, plus 10. And since there's no term over here that's being multiplied to both of these terms, you can opening the bracket is as simple as taking this outside the bracket after opening it. So this becomes x plus 4 whole squared minus 16 plus 10, x plus 4 whole squared minus 6.